Is everybody ready for the quiz today? Yeah.
I think we did chromatology and biolab yesterday. I think.
Chromatography?
Yeah, sorry.
Yeah.
Did we?
I don't know. I don't know what you do in biolab.
We put grape Kool-Aid through something, and then we put 5% acetone through it, and then 25% acetone through it after that. Is that?
Did you collect the stuff at the bottom?
Yeah.
Yeah, that's a type of chromatography. Yeah.
Also.
You loved it, didn't you?
It actually was kind of cool.
Yeah.
I love it.
No, you loved it. It's okay. So the first half of the class we'll continue the lecture on chapter 2, and then the second half you guys can log on to Canvas and then take the quiz. Okay, I think we'll go ahead and get started. So here's the plan for today. So in the first half of the class, the first 40 minutes, we're going to continue with chapter 2. And so the quiz becomes available at 9:10. So I'll stop a little bit before 9:10 so you guys can log on to Canvas. And then at 9:10, the quiz becomes available. It'll be available till the end of the class, which is 9:50. So that's a 40-minute time frame there. Once you open the quiz and start working on it, a timer will start and you have 15 minutes for the quiz, okay? So don't open the quiz until you're all set and you're all ready, all right? So you have a little bit of time there to get settled in, and then if you need it, before you open it. So that's the plan for today. Any questions about the quiz or any of that stuff? Hopefully everyone's used to going into Canvas and looking at stuff. And if you went in before, you saw that the quiz has been sitting there for a while. It's just not accessible until the timer starts. So hopefully we don't have any problems with that. Okay, so on Monday, this is where we left off, where we were talking about the periodic table and just some of the groups. The main ones were the 1A, 2A, alkali metals and alkaline earth metals, and then 7A, 8A, the halogens and the noble gases. So we're going to continue the discussion around the periodic table. So when we look at the periodic table, and if we look down in the lower right-hand corner, there is a nice picture of a periodic table. We see that kind of stair-step line, dark line in there, the stair-step over towards the right. That's the line that separates the metals from the non-metals. So everything to the left of that is metals. Everything to the right is non-metals. We'll talk about the ones that are a little different color, that kind of pinkish, purplish color that's right on the line. We'll talk about those in a moment. Metals usually have some similar type of properties. They're usually solids. As with most things in chemistry, there are exceptions. Mercury is a real well-known one. If you've seen mercury, that's a real dense liquid. But usually metals are solids. They can conduct heat and conduct electricity. And so you think of metals, you think of like copper wire for your electrical circuits and things like that. And they tend to be kind of shiny. And so there are some examples of metals down on the left-hand side, ones that we're pretty familiar with: iron, silver, gold, lead, things like that. As I said, the non-metals are on the right side, so kind of that upper right-hand stuff. The one that's kind of funny is hydrogen. So even though hydrogen is in the 1A group, it is considered a non-metal. And so non-metals in general, when we think of non-metals, we tend to think of carbon, nitrogen, things like that, the halogens. They can be solids, they can be liquids, they can be gases. It's a range of things. And the non-metals really are the things that when we talk about reaction chemistry and forming compounds and things like that in terms of reactions. So, you know, if you look around in the room and you think of the material the desk is made of and the carpeting and all that, that would be non-metals reacting to form organic compounds. As I said, that kind of step-like pattern you see over towards the right there, that's the line that separates the metals from the non-metals. And the ones that are highlighted in the different color, those are the ones that are called metalloids. And the metalloids are ones that have some properties that are metal-like, have some properties that are non-metal-like. So they're not as definitive one way or the other as the ones further to the left and further to the right are. So those are the three main groupings that we're going to talk about. the metals on the left, the non-metals on the right, and the metalloids in the middle. So when we want to represent what a compound consists of, we use a chemical formula. And the way we write chemical formulas are, we have the element symbol for whatever the atom is. And remember, that's either one capital letter or one capital letter and then one small letter next to it. And then we have a number. Unless the number is 1, we don't write a 1 in there. But if it's 2 or 3 or 4, whatever, and that tells us how many atoms of that element are in that compound. We have some examples over there. We see hydrogen is H2, oxygen O2. We see carbon dioxide is CO2, methane CH4. So what that's telling us, for instance, on the methane is that we have the 1 carbon atom, and then we have 4 hydrogen atoms attached to that carbon atom. And that tells us what methane is. And so if we think about some of the stuff we learned earlier, that tells us that if it's CH4, we always know that's methane. Because it doesn't matter where it is or what it is or whatever. If it's CH4, it has to be methane by definition. I think I've mentioned the term diatomics before. So diatomic molecules, there are certain molecules that when you find them, they're naturally occurring. They're 2 of the atoms bonded together, 2 of the atoms stuck together. And so these are some examples of that. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. When you find those around, you don't find just hydrogen by itself. It's always H2. It's always N2. It's always O2. And so we call those diatomic molecules. There's 2 types of formulas that we write. One is the empirical formula, and one is the molecular formula. The molecular formula tells us exactly how many atoms are present. So for each element that's there, it tells us that, and then it tells us how many of those atoms for each element are there. And so so from that, we could calculate the molecular weight of the compound and things like that. Empirical formula is just if you take that molecular formula and if you can somehow divide it by an integer to get it to go to a lower number across, you do that. And we'll see some examples here in a moment. So if you have the molecular formula, you can always figure out what the empirical formula is. But if you have the empirical formula, it's pretty difficult to figure out what the molecular formula is unless you have more information. Usually when people talk about formulas for compounds, you're more interested in the molecular formula because that's more informative than the empirical. There's some instances where you may be interested in the empirical formula, but that molecular formula really gives you more information about the compound. So let's take a look at some examples of what I'm talking about. So here's the molecular formula for glucose, C6H12O6. So what that lets me know is that there's 6 carbon atoms there in that molecule. There's 12 hydrogen atoms in that molecule, and there's 6 oxygen atoms in the molecule. It doesn't really give me information of how they're arranged, but it does tell me how many there were there. So one thing I could do is I could calculate the molecular weight of that by taking the atomic weights of carbon, hydrogen, and oxygen, and then multiplying them by the 6, the 12, and the other 6. So if this is the molecular formula, what would be the empirical formula for this? Any ideas? And how would I figure that out? So what I would do is I would look at the subscripts there, 6, 12, and 6, And I would say, is there some kind of common division I can do to that to get them lower? Yeah, we divide by 6. So then if we divide each of those by 6, it would be C. We don't write the 1, but it would be 1, and then H2, and then O. So that's what we were saying, is that if we have the molecular formula, we can figure out the empirical formula just by doing a little bit of math there. But if I told you the compound was CH2, unless I gave you more information, there's no way you would figure out that that was glucose. Okay, so caffeine, C8H10N4O2. So once again, this is telling us in that caffeine molecule, there's always going to be 8 carbons, 10 hydrogens, 4 nitrogens, and 2 oxygens. So it doesn't tell us the structure of it, but it tells us what atoms are in caffeine and how many of them. And once again, we could get a molecular weight out of that. How about this one for empirical formula? Do we see any common math we can do to lower that?
Divide by 2.
Yeah, divide by 2. So then we have C4, H5, N2, and O1. And sure enough, that's what we get. So empirical formula is kind of like this lowest common number thing that we can have. Molecular formula is the actual formula for the molecule. So we can get, if we have the molecular formula, we can figure out the empirical formula. If we have the empirical formula and that's all we have, we really don't have a way to figure out the molecular formula. So does everyone understand the difference between molecular and empirical formulas? Okay. So the molecular formula is nice. It's nice to tell us, especially when we're trying to calculate molecular weights, what we're dealing with. But there's a lot more information about the molecule that we may be interested in. And so because of that, there's different ways that we can represent and draw molecules and represent molecules. And what we're looking at here are just some of those ways. So on the left there, this is methane that we're looking at. On the left is the molecular formula, CH4. So from there, what we learn is there's 1 carbon, 4 hydrogens. So we could figure out the molecular weight. The next one, where you see the carbon with the lines and then a hydrogen at the end of the line, that's starting to show us the structure of the molecule. It's just a one-dimensional structure because it's just sitting on the paper. But what it tells us is we have 4 hydrogens bonded to that carbon. Okay, and this is a pretty simple molecule because we just have 2 atoms but when you get to more complex molecules, this is really helpful to see where different atoms are attached to other atoms. Well, even that doesn't tell us everything we would like to know about methane. And that's where this next one, which they call perspective drawing, and really the next 2 after that as well, what those start to do is they start to tell us what is the shape of things, kind of put it into that 3-dimensional look. The perspective drawings, one thing you always see with those is you see kind of the little triangles there on 2 of the hydrogens, and one triangle is colored in, and the other triangle is kind of like those dashed lines. That's by convention, is that you're supposed to assume that the colored triangle then means that's coming out towards you on the page. So if we did have the ability to have a 3D projector, it would be sticking out at us. The dashed line triangle, that means it's going back into the screen. So think of it, that introduces like a 3D perspective, because what we know is that for this molecule, it's not a flat carbon with 4 hydrogens on it. It's a carbon, and then these hydrogens are arranged in space. A little later this semester, we'll learn what we call these different shapes, and we'll study these shapes in more detail for different molecules. The next one over there, the ball and stick model, is a similar thing to the perspective drawing, but there, and this used to be big back when I was in college and your age, is we used to buy these little model kits, kind of like Tinker Toys or Legos or however you want to think of it, and you would actually build the molecules. And you really would have these little balls like that and little sticks, and they would go on, and you'd really get a feel for the 3-dimension that the molecule is. That's what that one is. And then finally, the last one, the space filling model, is if you think about it a little bit, when we talked about the nucleus and then the electron shell kind of around it, and there was like a space component to it, this is trying to give you a feel for the space. So the size of the atoms, the space they take up, things like that. So these are all different ways of, in this case, showing you and expressing methane. The ones that you use kind of depends on what you're studying and what you're trying to prove. If you're doing just normal balancing equations and things like that, you tend to use the molecular formula. That has all the information you need to kind of do that. You might use a structural formula if you're studying reaction chemistry and you want to start moving electrons around and move functional groups around to see how things react and how things move and form and things like that. Maybe you use the structural. Some of these 3D models, which are those last three, you use those when you're trying to figure out bond angles and bond lengths and things like that, where you need a little more accurate visual representation. So each of these has a purpose. It kind of depends on what you're doing. We'll do a lab later in the semester, a computer-based lab, where we look at some of those last two type things, especially the last one, the space filling. And what's neat about that lab is the software allows you to rotate molecules around, so you can get different views of it and things like that. So that'll be later in the semester in the lab. But then you'll get a feel for why you would want that versus, say, the first one, the molecular format. So when we talk about the compounds, there's always the regular organic type compounds. And as I said before, those are the ones that we do most of our reaction chemistry with. But there's also a group known as ions. And the ions are formed when you have something either gaining an electron or losing an electron. And so you see on the left there, we have some examples of cations, and the cations are usually metals, and the anions over on the right with the negative charge, those are usually the nonmetals. If it's a cation, that means that it has lost an electron. If it's an anion, that means it's picked up an electron. So if it's +1, it means it's lost 1 electron. If it's +2, it's lost 2 electrons. By the same token, if it's -1, it's gained an electron. If it's -2, it's gained 2 electrons. And where does this minus and plus stuff come from? Well, remember what we said before is that all of these atoms have a set number of protons, right? And that's what determines which atom it is how many of those protons are there. So we can't lose protons, because then that would violate some of those early laws that we learned, that you fundamentally don't change the atoms. But if they pick up electrons or lose electrons, which they can do, then you create these atoms or these ions. And so the cation is positive because you have the plus charge coming from that proton, and now you've decreased one of your electrons, you've decreased one of the negative charges, so now you have more positive charge. That's remained constant. The negative charge has gone down by 1, so that's why it's positive. And then same type of thinking for the anion. you have a certain number of protons and electrons. The proton number is not changing. As you add electrons to it, it picks up electrons. Then you have a more negative charge than you do positive charge, and so the result is a negative ion. So the idea between cations and anions, really an important concept. And so if you look at this little miniature periodic table up on top, and you see the charges on these ions, you should memorize all of that. You should know that chlorine wants to be a -1. You should know that lithium wants to be +1. You know, we talked a little bit about trends in the periodic table and things like that. Does anyone see anything with these ions that might be useful in remembering this instead of just straight memorization? Are you seeing any trends up there?
The ones that share a group normally share a charge.
Yep, exactly right. The ones that share the group share the charge. So if we look at 1A, for instance, all of those are typically +1. That's handy. 1A +1. The second one, magnesium, calcium, on down the line. Group 2A, they're +2. So for me, I don't necessarily remember what sodium is or potassium is or rubidium, but especially rubidium, because that's one you rarely use. But I know it's in 1A, and I know the 1As are +1. Same thing with 2A. Calcium is one I maybe do a fair amount with, but strontium, oh gosh, I never deal with that. But it's in that column, so I know it's 2A. Same thing over on the right there with the 7A, so the halogens, and then the 6A. We got -1 for those halogens, -2 for oxygen, and those in that 6A group. So there's an example of using the periodicity of the periodic table to help me remember what some of this stuff is.
I have a quick question. So is it just saying that how many electrons it wants to get rid of or it wants to give away or take? Okay.
Yep, that's what it's saying. And a little later in the semester, we'll get into what exactly that means. But for right now, yeah, that's what it's saying. Is that different atoms have a different propensity because of their electronic structure to either give up or accept a certain number of electrons.
Thank you. Okay, that makes sense.
So here's some common cations. The ones that are bolder are the ones that we're most likely to talk about in the class. So as you go through memorizing, definitely make sure you know the bold ones before you worry about the others. Ammonium there, ammonium ion NH4 plus, we'll talk about what that means, why that's we'll talk about why that's not just an atom, but it's a functional group. Here's the +2s, some of those that you see quite a bit often, and then aluminum and iron 3 and chromium 3 and some +3s down there. Some of the common anions that you'll come across. Once again, we have some simple element anions, and then we have a little bit more complex anions as well. And we'll talk in a few minutes about how we name these. So hopefully you're starting to get a feel for everything we've talked about so far today is basically stuff you got to memorize. So conventions on how to name things, some of the charges, and so this is stuff that we're still kind of in the memorizing portion of the class. So I mentioned the ammonium ion there, NH4. And so there are groups of atoms that can either pick up or lose electrons. And these are called polyatomic ions. So polyatomic just means more than one. Technically, you could call it more than two, but I think of it as more than one. And so a common one for the cations is the ammonium ion. So NH4 plus. A common one for the anions is sulfate, SO4 minus 2. So if ammonium is NH4 plus, did that gain an electron or did it lose an electron to form that ion?
Lost one.
It lost one, right? Because for both that nitrogen and hydrogen, we know the proton number didn't change. That's going to be the constant. And that's all positive charge. So in order for the polyatomic ion, the ammonium ion, to have a positive charge instead of neutral, it had to have lost an electron. How about the sulfate at -2? Did that gain or lose electrons? Gain, because it'll start out as neutral. It picks up 2 electrons. That's 2 negative charges to give it the overall negative charge. So we talk about losing or picking up electrons. Another way that people will express that is they'll talk about donating electrons and accepting electrons. So just those terms are kind of used the same. They all mean the same thing. So when we talk about compounds, we talk about molecular compounds, which tend to be those organic type compounds with carbon, hydrogen, nitrogen, oxygen, things like that. And then we also have something called ionic compounds. And ionic compounds are the ones that are typically formed between a metal and a non-metal. And so here we have an example of sodium chloride. So we have the sodium, which is a metal, because that's over on the left-hand side. And we have chlorine, which is a non-metal, because that's over on the right side of the periodic table. For these type of ionic compounds to be formed, we have some type of transfer, electron transfer happening. What did we say about metals? Do they like to accept electrons or donate electrons?
Give off electrons.
Yeah, we said that the metals like to give off or donate electrons. We said the non-metals like to accept electrons, receive electrons. So it's kind of like a match made in heaven. You got one guy who wants to give up electrons, the other one atom who wants to receive electrons. And it's that willingness to give up and receive electrons that make it possible for these compounds to form. We talked also about how opposites attract. So because they're oppositely charged now, based on their propensity to either donate or pick up electrons, we get that association. So it's not quite the same as the regular bonding that we have in the other molecules, but it is an attraction there. With the ionic compounds, you typically only write the empirical formula. And that's because, it's mostly because that's really what's going on in these inorganic compounds tend to have this, what they call lattice structure, which they kind of have a picture there, where you see the molecules kind of, the atoms and molecules kind of stacking together. But we don't express it all that way. We just give you the empirical formula. So the ionic compounds are one example of where empirical formula is more useful than the molecular formula. This is similar to what we saw before, where they highlight some of the more common cations and anions, and this is what I was saying, you should know these. These are ones that you see all the time. We want to memorize this, and let's take advantage of seeing, once again, that 1A, all of those are a +1, 2A, a +2. And so if we remember, metals are on the left. Metals want to lose electrons. They want to donate electrons. So that gives us a feel for those things on the far left are going to be positively charged. 1A, 2A, that's telling us +1 or +2. Same thing over on the right there. Let's focus on 7A and 6A. And we see once again, non-metals want to pick up electrons, want to receive electrons. So that gives us a negative charge. That 7A column, all -1, 6A rather, -2. I'll just mention the noble gases for a moment. The noble gases don't like to pick up or lose electrons. At one time, and you don't see it much anymore, that 8A column was called the inert gases. And so now they tend to just call it the noble gases, but those don't really do much of anything. Let's talk about writing formulas for these compounds. So unless we're told the compound has a charge, it's electrically neutral. And so in this case, we have magnesium and we have nitrogen. And we're saying the magnesium charge is +2 and our nitrogen charge is -3. So if we're combining these two atoms together, how do we know that it's Mg3N2? Well, an easy way to do it is if we see that +2 on the magnesium and -3 on the nitrogen, we need to make it so it balances. And so we can do that by then taking the +2 and making it the subscript on the nitrogen, and the 3 on the nitrogen and making it the subscript on the magnesium. So then we get to Mg3N2. And we can go back and check this to make sure what we did is correct by saying, if I take 2 times -3, I get -6, right? If I take 3 times +2, I get +6. +6, -6, neutral charge for the molecule. So when you go to write these formulas like this, if you know the charge of the atoms, like I said, in this case, +2 for magnesium and -3 for nitrogen, and then we put our subscripts down, we can go back and check, and if it doesn't balance out neutrally, then we know we don't have it right. If it balances and is neutral, then we know we've done the right subscripts on the compound. So how many of you heard the term nomenclature before? Okay, we have a few people who have. So nomenclature is just a fancy word for how we name the stuff. So you'll hear people talk about chemical nomenclature, and what that means is there's certain rules that have been adopted in the chemistry world of how you name compounds. And we're going to start going over some of this. And this is all stuff that is, to be honest with you, it's just memorization of memorizing what the rules are for how to name the compounds. It's kind of like learning a language. A long time ago, someone defined certain things of how they're going to be named, and now you just need to memorize it so that you understand what people are talking about. So it's kind of like this is the language, this is the chemistry language. So we're going to learn how to name ionic compounds, acids, binary molecular compounds, and we'll do a couple examples of organic compounds. The two we'll look at are alkanes and alcohols. If you take organic chemistry in a year or two, you'll learn all the tricks about naming the organic compounds. So for inorganic nomenclature, and so if I'm talking about an inorganic compound, what does that mean?
It doesn't contain carbon.
Right. And so if I'm naming an inorganic compound, we write the name of the cation. if the cation has more than one possible charge, then we want to indicate which charge it is in a parentheses. So with a Roman numeral. If it's just, there's just one charge to it, you don't have to do that. But a few of them have a couple different oxidation states, and so they have a couple different charge choices. If it's polyatomic, it'll end in IUM. So ammonium is an example of that, right? So ammonium is an example of a polyatomic cation. If the anine's an element, change the ending to I. If it's polyatomic, just simply write the name of the polyatomic ion. So an example of that would be sulfide or sulfate, things like that. Okay, when we have oxygen present, these are called oxyanions. And so if you have two oxyanions with the same element, the one with the fewer oxygen is called ite, and the one with more oxygens is ate. So here's two examples of this. So NO2 minus, so it's an anion, it's an oxyanion because it's got the oxygens, and nitrite is what that is because it's the lower of the number of oxygens. Nitrate would then be NO3 because you have 3 oxygens there rather than 2. So oxyanions, you have oxygen present, you have a couple different choices of how it can be based on the oxidation state, in this case of the nitrogen. And then another example is sulfite and sulfate. So SO3 minus 2 is sulfite. You have that additional oxygen in sulfate, so that's SO4. And so the one with the higher number of oxygen ends in 8. The one with the lower number of oxygens ends in 9. So the nitrite, nitrate, sulfite, sulfate, this is real common type of stuff in inorganic acids. So you probably have heard of sulfuric acid, for instance. So that would be H2SO4 on the sulfate. And so we'll talk about the acid formation also in a bit. But for right now, let's go ahead and stop here and let's get ready for the quiz. So go ahead and log on to Canvas, please, and get set up for that. And then once you're set up and ready to go, start the quiz. That'll start the clock on the quiz. You got 15 minutes to complete it.